Hi, this is Michael Gasvoda, and I will be presenting my project for the IBM Coursera Advanced Data Science Capstone course, English Character Recognition with Keras and Scikit-learn. We'll begin with the general project overview, covering our data, use case, the solution implemented, and next steps, and then proceed to a more technical overview for fellow data scientists, where we will cover architectural decisions, data quality, and model performance, as well as a demo of the model output. This presentation used the CAR74K dataset from TD Campos at the Microsoft Research Center for India. This dataset itself is quite large, with over 74,000 images of various types across 64 classes, including 0 through 9 and the letters A through Z, both capitalized and lowercase. This includes both handwritten and generated images. The immediate output of this project is a classifier that can be used to recognize handwritten and digital characters in images. This could be expanded to act as a feature extraction method for getting strings of text from video and images, and as input into further algorithms for rich content interpretation engines. The target solution for this project is a deployed model serving an API endpoint running on IBM Cloud. This endpoint could not be fully set up for technical reasons that I'll go more into detail on later, but a package has been compiled that can be hosted in serverless frameworks on either IBM or AWS clouds. API endpoints with serverless compute have a number of advantages, including very low cost compared to the standard reserved server space, ease of use and access for end users, and built-in resilience and scalability that are features of the hosting platforms. They also come with many built-in security and access features thanks to the infrastructure providers themselves. Other potential deployments of this solution could be as a plugin or other embedding in a video or image processing software for dynamic feature extraction as mentioned above. We will now dive a little deeper into the technical aspects of the project, beginning with some design decisions. There are two primary design decisions I want to highlight. The first is about modeling frameworks and algorithms. For the deep learning model, I chose to use Keras, implementing the AlexNet architecture. Keras was used as it contains all the necessary details I wanted to tweak without requiring the complexity of dealing directly with TensorFlow. It also has several image processing utilities which were very important in preparing the image for processing. AlexNet is a popular convolutional neural net architecture and has a record of strong performance on image classification tasks. This model architecture won the ImageNet competition of 2012. While there are several newer frameworks that exist today, AlexNet trains faster than most and offers an appropriate balance of training speed and performance for the hardware and budget limitations of this project. Scikit-learn is the de facto standard for most non-deep learning tasks. While Spark is more thoroughly covered in this course and offers a great alternative for working with large data, the limited instance size of the IBM free tier used for training limited my ability to use their system. I was able to use Scikit-learn on a desktop with more memory to train on a larger set of data than I would have been able to with Spark, although I still had to limit the input image size to avoid memory errors in this environment. Support vector machines generally perform well on classification tasks and provide a strong baseline classifier. With image work, however, convolutional neural nets are much more accurate, so the Scikit-learn classifier is used mostly as a point of comparison. In the end, the Keras model outperformed on almost all aspects, achieving much higher accuracy and lower training times than the Scikit-learn model. The downside, however, is that as with all deep learning models, the process is less open to introspection and harder to explain to decision makers. The second main decision came with deployment options. IBM Watson Studio offers an option for deployment of models via Jupyter Notebooks, as well as creation of a REST API endpoint integrated with the serverless compute service. Jupyter Notebooks are very easy to build, maintain, and distribute, but offer less flexibility and a less friendly interface to end users who may seek to use this as part of a larger application. A REST API, on the other hand, takes a little more work to set up and may involve some costs, but it integrates well with a wide variety of other programs and is very easy for the end user, making it the stronger option in this case. I will note that in this case, as mentioned previously, I created a deployment package for OpenWhisk, which is the underlying platform used by the IBM Cloud, but due to the size of TensorFlow as a dependency, I was unable to actually create the serverless function. This package, however, could be used on AWS to create the endpoint and could be used on the IBM cloud if upload size policies change in the future. Finally, for model performance, candidate models were scored on simple accuracy. Given the large number of classes, this is a simple to compute and explain metric. The prepared dataset offers a balance of class distributions, which satisfies many of the arguments towards using metrics such as F1, which offset imbalanced classes, and the metric is available in both Keras and scikit-learn. Alright, so I'm going to walk through really quick some of the more detailed model overview. So here I have the tensor board pulled up. One of the advantages of training in Keras is they output these nice visualizations. So what we can see here is there is a small but noticeable positive trend in accuracy over time, as we would expect, and a negative trend in loss. Again, we're using simple accuracy as our metric here, and this is categorical cross entropy for our loss function here. With our validation accuracy and loss, we only trained for 3 epochs, as each epoch takes a little over 45 minutes, so it's quite computationally intensive. But we can see a slight but noticeable increase in our validation accuracy and decrease in our validation loss as well, so that all looks great. If we hop over into Jupyter Notebook, we can look a little bit deeper into some of the outputs of the trained model. In this case, we're looking at the Keras model, the AlexNet that was trained for 3 epochs that performed the best out of everything tested. So here we have a simple utility function to show an image that's being processed if we want to feed it a new image and see what it predicts for that. In this case, I'm using a computer-generated image of a C. So we feed it a predicted image and we get the output that we would expect. It resizes it, does some other simple processing in this function, outputs the expected class right here, or the predicted class, excuse me, and then the expected class is in the file name. So in this case, it does predict it correctly. If we go through to the image data generator and run our entire test directory, that's going to be testing on 7,400 images. If we generate that and plot a confusion matrix, we'll see again about what we would expect. We see a nice deep colored line down the middle. That means all of these spots here being classified correctly. We also see a couple areas where it's not performing quite as well. A lot of these are going to be in capital and lowercase characters that are very similar. So for instance, it mixes up lowercase and capital C, lowercase and capital V, characters that can be very similar and very easy to confuse. We also have O and 0 get confused sometimes. So these are all abnormalities that we expect given the domain of the problem. And then just for another simple step of verification, we import the scikit-learn metrics and calculate those. Again, scikit-learn is showing that we have an accuracy score of just over 80% and F1 score of the same, which we expect because we have a balanced class distribution in our training set. And the evaluate gener from Keras gives us just about the same values, a little over 80% for your accuracy, and a loss value of just about 0.61. Finally, we'll hop over into the actual deployment. So I mentioned that we are using a script that could be packaged and deployed in a number of different ways. But for here, I just have a simple CLI interface. So we're going to load up a simple image from our test directory. In this case, we're going to be testing it on a computer-generated 9. We're going to execute the script, pass that in as an argument. It's going to take the image, resize it, make sure that it has the proper number of bands and all of that. And then it's going to output our prediction here. In this case, it does predict a 9, so it is predicting correctly. This concludes my presentation. Thanks for taking the time to watch, and have a great day.